have you ever stopped to think about how we prove something that starts with a big if? You know, how logicians and even computer programs can build a solid argument on a temporary idea? Well, today we're diving deep into a really cool concept that explains exactly that. It's all about the art of reasoning with assumptions. Let's get into it. Here's the plan. We'll kick things off with those ifs in logic. Then we'll get to the main event, this wild idea of holes in proofs. After that, we'll see how this all connects to computer programs, ask if there's another way to think about it, and finally, wrap up with why this principle is such a big deal. All right, first up, let's start with that fundamental building block of so many arguments, the assumption. I mean, really think about it. If you want to prove a statement like, if it's snowing, then it must be cold, you have to start by just assuming it's snowing. For a moment, you pretend it's true. But that's tricky, right? How do you handle these temporary truths without getting them mixed up with actual proven facts? That's the central problem here. So in the world of formal logic, these ifs have a name. They're called assumptions. They are not facts. They're temporary placeholders. Think of them like scaffolding you put up to build a wall. You need them to get started, but they aren't part of the final structure. They're essential, for sure, but you've got to manage them carefully. Okay, so let's get to the core concept for today. It's a really powerful way to visualize how these assumptions actually work. It's called the placeholder principle. This idea comes from a specific area of logic, and the main point is to treat assumptions as, well, secondary characters. They're helpers in the story of a proof, but they are not the main heroes. And here's the killer analogy, the thing that makes it all click. This principle says we should think of assumptions as holes in proofs. Just picture it. Your argument is this solid, logical structure, but everywhere you used an if, everywhere you made an assumption, there's a gap. A hole that needs to be dealt with before your proof is complete. So you've got these holes. What do? Well, you've basically got two options. Option one, you fill the hole. If you can cook up a separate, solid proof for your assumption, you can just plug it right in. Simple. Option two is a bit more subtle. You withdraw the assumption. Certain logical rules let you neatly package up the if part of your argument, which makes the hole just kind of vanish. Now, I know this might all sound a little abstract, but this placeholder idea has a mind-blowing parallel in a super practical field, computer science. And this connection, it changes how you see both of them. This link is so deep it has its own name, the Curry-Howard Correspondence. It's one of those profound discoveries that acts like a bridge between two worlds, showing an incredible structural link between mathematical proofs and the programs running on your computer right now. And this just lays it out so clearly. An assumption in a proof? That's literally the same thing as a variable in a program. It's just a placeholder waiting for a value. A complete, solid proof? That's a working program. And the process of simplifying a proof, which logicians call normalization, is exactly the same thing as a computer running a calculation. It's the same structure, just wearing different clothes. But you know, like any great idea in logic or philosophy, the placeholder principle isn't the only game in town. This is very much a live debate, not some ancient, settled fact. Which naturally leads to a really important question. Do we have to see assumptions as these secondary holes? Is this perspective absolutely necessary for logic to work? And the answer from a good number of logicians is a firm no. They argue you can build totally valid logical systems that are way more assumption-friendly, where assumptions are treated as first-class citizens. At the end of the day, it's a choice you make when you're designing the rules of your logical system. So, after digging into the theory and even the debates around it, let's pull it all together. Why does any of this actually matter? What's the big deal? Well, the simple answer is that its influence is massive. This whole perspective on assumptions isn't just some dusty philosophical point. It has real, concrete, far-reaching consequences in the super technical fields of proof theory and computer science. I mean, the ripple effects are everywhere. This principle helps create cleaner, more elegant rules for closing off those if statements we talked about. It's at the heart of major debates about what a proof even means. It's led to wild advanced systems where you can assume entire rules, not just facts. And it's a foundation for methods that automatically simplify proofs, which, as we just saw, is a whole lot like optimizing computer code. So all of this leaves us with a pretty fascinating thought to chew on. If a logical proof really is just like a computer program, then what are the paradoxes and contradictions of logic? Are they just bugs in the code that we haven't found yet? And what would it even mean to debug our own reasoning?